let's continue on. Let me do one more thing using this same example. In this problem, I could be asked about maximum height above the cliff or above the release point. In the problem, it could say, hey, if the person is standing here and they throw it upward, what's the maximum height that the ball reaches before it starts moving back down again? And we can do that pretty easily. The only question is going to be, does the question ask, do they want the max height from where the person is standing, or do they want the maximum height above the lowest point of the problem? I'm going to say for this example, just what's the maximum height that the ball or object or stone, whatever, will travel above the person. So we're going to ignore all this cliff down here. We're going to go here. We're going to still call this y1, where the object starts, where the person throws it. But now y2 is no longer there. Y2 is going to be up here, where the object reaches this apex at the top. So, the ball goes, stops, and then starts to fall back downward again. And that's important. That's important because that moment of instantaneous velocity of 0, when the object changes direction, is extremely important and can be utilized in any number of cases. The ball moves up, or the rock moves up, or whatever moves up. Before it turns around and goes the other direction, it has to stop just for an instant. And then comes back down. Now, when this object stops, don't think acceleration stops. Acceleration does not stop, because if acceleration stopped, the object would then, when it reached maximum height, would just sit there and float. That doesn't happen. Everywhere, all the time, is being pulled down with an acceleration of 9.81. So don't think just because speed goes to 0, velocity goes to 0, that acceleration also goes to 0. No. No, not the case. So, but this changes our information. Okay? What's the maximum height? I don't know. New problem, new scenario. Just because they mentioned the 10 here falling in the cliff, if they say what's the height above the person when they released it, it's a whole new section of the problem. When every section or part of the problem, if the problem talks about 2 different positions compared to the previous part with 2 other different positions, you have to restart the problem. Restart your data. Okay? So, I'm going from here to here. I don't know what that change is in displacement. I know it's up. That's a good thing. I do know that I threw it upward. I do know as it travels upward, it's still the same acceleration. It's going to be pulled down, or try to be pulled down, which is going to cause the object to slow down, and eventually, and the most important part here is at the very top, at the apex of flight, we do know one piece of information. That this final velocity at that position will be 0. And that won't be given as a number in these problems. That's, again, another conceptual thing you have to just know. At the top of flight, the velocity for a moment will be 0. As the object falls, acceleration will always be 9.81 downward in a free fall situation. Those numbers are not given to you, but you must be able to know them and apply them, given those phrases. Well, now, since I have these things, and I want the maximum height, I can find it. I can find that maximum height. And again, I don't know the time, but I can get away with not knowing the time with this particular problem. we happen to know that velocity 2 is 0. So a lot of the times if I know something's 0, I'm just going to cross out the variable from this point forward. V1 was at positive 6. There's no tricks with square roots or anything here. So we're just going to go and solve it. It's going to be 36 divided by, and the negatives will cancel out because this object is moving upward. So 19.62, 1.83 meters. I skipped some of the math steps, but you should have been you should be able to go back and follow that. All right. You should be, if you were asked, you should be able to go and find the time. By the way, that would be time to maximum height. That's easy to find. Sometimes a problem may ask you to find this information. Sometimes a problem will ask you to find the displacement. They may not ask you to find time, and if they don't ask you to find time, you don't need to find it, even though we have a blank spot in the data. So if they don't ask for it, don't do it. All right, good. All right, we have one more thing to discuss regarding free fall. That's the graphs, the distance time graphs and the velocity time graphs. And I think that's enough, more than enough to get you started with these types of problems and analysis. Okay, so the last piece that we have to deal with, free fall, is displacement time graphs and velocity time graphs, just like previously. And we will have more practice on these kinds of graphs, but with a free fall graph, you will notice here, for displacement time, I made y1, when I was standing on the cliff, I made that equal to my height being 0. And so if I create a distance or displacement graph regarding that, now yes, it's a y motion, not an x motion, doesn't matter. If I do that, no, I start off throwing the object from 0. And I threw the object upward, so it did go upward, 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 upward to a maximum height. And we calculated what that maximum height was. But at that maximum height, which I'm going to call T2, that happened. It was like 1.8 some meters or something like that. That is when we also stopped for a moment, for a brief, instantaneous blink of an eye moment, because we were turning around. And we are, no. We're moving up, 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 and then we're going to start moving back downward. Now, we're not negative region yet, but we're moving downward. And by the way, you'll notice that this curve is nice and parabolic because it has a constant acceleration. And constant acceleration graphs for displacement time always have that nice parabolic shape. So when I start to turn around at T2, I stop for a moment. I do eventually come back down. I got to pass the starting point, right? What goes up comes back down. So it goes up and then back right past where I let it go from, and then continues downward. So that has to be represented. It goes up, stops, hits the point of where I let it go, and then keeps on going below the cliff. So there's a couple important times there. When it stops at the height of motion, and then when it passes by where I released it from. Now, this graph has a corresponding velocity time graph. And those important aspects and moments of time and what's happening at those times better match. I release the object. At time 0, I let it go at 6 meters a second. Now remember, that's 6 meters a second. As soon as it leaves your hand, it's not in contact with your hand anymore. It's the moment that it just pops off your hand. So 6 meters a second upward, it's slowing down, slowing down, slowing down, slowing down, slowing down, and it stops. That stopping time better match when it was at maximum height. That time had better be the same. And then it starts turning around. Yeah, it's in the positive region of displacement, but it's moving backwards now, so it better have a negative speed, and it is speeding up. So it was slowing down, stops, speeding up. Now, when it reaches this point at T3, when it reaches the height at which it was released, notice its speed better be the same, but in the opposite direction of when it was released. We released it at 6 meters a second upward. When it reaches T3, it better be about 6 meters per second downward. If I catch something at the same height it was released, if I throw it up, bring it down, it should have the same exact speed because it's going to slow down and speed up at the same rate as it travels. So if it goes up the same distance in the same time as it comes down the same distance in the same time, the change in speed had better be the same, except instead of up, it is down. So I release it at 6 up, as long as it's straight up and down, not at a wacky angle though. We'll talk about that next unit. Up, down, catch it at the same height. Now it has to be at the same height though. If I catch it at a different height, it's different speeds. So you got to be careful there. But if I release and I release it at a height, if I release it at a starting point with a speed, and it goes and comes back down to that same starting point, coming downward, those speeds should be equal but opposite. But we didn't catch it there, we let it go, and it continues to speed up in the negative direction. So you're going to have to use your knowledge of distance and velocity time graphs, combine that now with realistic situations of free fall, so you can interpret those graphs, and that those times of significance had better match. If this happened, I forget what the time was here, 1.8 something seconds, is that what we said? I'll have to rewind the video, or if I'm wrong, please use the time we found before, correct me. A distance, no, we didn't know the time. We know the distance was about 1.8 something upward. So I didn't calculate that time. But whatever that time is, would be the same time here. Okay? All right. I hope that it makes good enough sense. I don't feel like going and calculating these values, but the concept should be there. And like I said, over the next several days, we're going to practice and apply all this wonderful knowledge. Thank you.